Hi, and thank you for choosing to listen to our talk. Together with my colleagues from Google Speech team, I'm delighted to share with you our thoughts on the topic of how might we create better benchmarks for speech recognition. Our motivation behind this question is to better evaluate automatic speech recognition, or shortly ASR systems, and that this will help them to work well for all people in all environments. The usual metric that we use to assess ASR quality is word error rate, that can be roughly understood as a percentage of the mistranscribed words. And if we take a look at the literature covering recent advances in ASR quality, the reported word error rates for English ASR systems actually look very impressive. Some of the used test sets include LibreSpeech, Timid, Switchboard, and others. And indeed, some ASR systems achieve very low word error rates. For example, 1.4 on the clean subset of LibreSpeech. While these results are indeed very impressive, they do not always reflect the real-life performance of ASR systems. For example, quality might vary depending on the language variety of the speaker. Also, low word error rates on those test sets do not always reflect how well the system generalizes to other domains, such as dictation or movie captioning. And another aspect is the processing speed of the system, and it is not reflected by the word error rate score. So ASR benchmarking is definitely a challenging topic, and a thorough evaluation involves more than getting a good word error rate. And indeed, Woodhardt's law applies here as well. When a measure becomes a target, it ceases to be a good measure. So in our talk today, our main objective is to imagine a step towards a better evaluation of ASR systems. Our talk comprises three parts. Firstly, we will look into what types of data we need to evaluate ASR models better. We propose selecting test sets from various domains, such as dictation, conversation, podcasts, audiobooks, and others, and also making sure that various challenging real-life factors will make it into the test sets, such as the presence of domain-specific terminology, various speaking rates, acoustic environments, and so on. Secondly, we will survey metrics that are important for the evaluation. We discuss word error rate and its varieties, but also go beyond word error rate, covering the latency, real-time factor, and several other metrics. In the third part of our talk, we envision a way to ensure that ASR systems work well for everyone. It involves representing language variation for diverse population groups, because language varies depending on the dialect, gender, age, and many other factors. And in order to understand the disparity of the speech recognition quality for those population groups, we propose a population-weighted ASR quality evaluation framework. The steps we propose are by no means exhaustive, but they could be helpful in setting up better benchmarking for ASR systems. Let me start by talking about ASR applications and related technical challenges. Ideally, a benchmarking test set would cover real-life scenarios and challenges that ASR systems face. While there is a wide range of those, we can roughly map the challenges to horizontals, domains and use cases, and verticals, conditions and challenging factors. Under such perspective, horizontals include ASR use scenarios, such as dictation, meeting transcriptions, captioning movies, and voice control, and so on, among others. And verticals, in their turn, include style and content of the speech. For example, terminology, speed, background noises, and acoustic environment, and also encoding formats. And of course, an ideal benchmark would cover as many of these factors as possible. One of the horizontal domains is dictation. It is also one of the first successful commercial applications of ASR systems. Sometimes it is a product by itself, and sometimes it can be a part of a bigger pipeline, such as speech translation systems. Typically, dictation involves a single speaker who might modify their speech patterns a bit. For example, they might speak slower than usually. Medical dictation is one of the subtypes of the dictation domain. It is used by medical professionals to simplify note-taking and therefore save them some time. A big challenge here is the support of the domain-specific jargon, with new names of the drugs constantly appearing on the market. And another area of dictation is the dictation practice that is frequently used by language learners. Many of such applications provide pronunciation feedback, and providing comprehensive, high-quality feedback is, of course, a challenging task. Other situations when people communicate with technology include voice search, control, and interactive voice response systems. When someone calls hotline or tech support, they frequently first talk to the IVR system that helps to gather the initial information from the caller. Its task might be to understand the type of the issue and redirect the caller, or maybe record their account number. Such systems help to reduce the workload of human assistants, and in some cases, they even can resolve issues on their own. A voice search and control usually involves shorter queries. The intent could be to access some information. When is the next Chinese New Year? How tall is Michael Jordan? Or maybe the intent of the user is to invoke an action, such as put a timer for 15 minutes. Similarly to dictation, such types of speech display some human-to-device characteristics, such as slower speech. Also, certain settings in this context involve an increased frequency of some semiotic class tokens. Among them, one of the most frequent ones are numbers. My customer number is 118356 and so on. Times and addresses. Navigate to 26 Long Street. Horizontal challenges also involve transcribing other types of domains, such as meetings, podcasts, movies, and shows. In particular, transcribing meetings is helpful for accessibility and bookkeeping, thus simplifying the note-taking process. Human-to-human conversations actually might be more challenging for ASR systems, since they usually involve spontaneous speech, including higher rate of speech, disfluencies or corrections, something like, they gave me this, how do you call it, I-494, oh no, I-24, and other types of challenges, such as overlapping utterances, turn-taking, and interruptions. When it comes to transcribing video content, there are two main approaches. One is subtitling. In this case, the whole show or movie is available at the time of the recognition, and the transcript might involve nonverbal cues or marks, such as loud music, sounds of the wind, and so on. In some cases, such subtitles are post-edited by humans to further ensure their quality. Another approach to transcribing video content is closed captioning. And this is a streaming task when the transcript hypothesis should be outputted as early as possible, simultaneously with the video being aired. The quality requirements are usually lower in this case, and this might be used, for example, for live TV broadcasts. And another growing area of ASR applications is podcast transcription that is already resulting in the creation of new test sets. So the previous slides outlined horizontals or various domains of ASR applications, and verticals refer to technical challenges that ideally should be reflected in the ASR benchmarks as well. For example, there should be a sufficient presence of the terminology and phrases from various areas, such as medical and historical terminology, as well as other domains. Also, since language is constantly changing, the ideal benchmarks should include new words, such as doom scrolling, for example. People speak with different speaking rates, and it might complicate the recognition of words, sentence boundaries, and speaker turns. Also, recognition rates might differ depending on various noisy acoustic environments, such as different recording settings. It can be real life or phone conversations or video calls, for example, and various levels of the background noise. And additionally, the diversity of the encoding formats presents a challenge on its own, namely different audio encodings, codecs, and non-standard sample rates. While in a previous section we outlined various domains and challenges that we propose to include in the ideal benchmarking test set, here we outline metrics that are important to track the quality of ASR systems. So to begin this part, let me come back to the topic of word error rate, since this is the most popular ASR quality metric. Word error rate is calculated as follows. So the numerator is the number of words that were transcribed incorrectly, namely, words that were substituted by some other words that were inserted in the machine transcript but were not there in the ground truth one, and words that were there in the ground truth transcript but did not make it to the machine. and the denominator is the sum of all words in the ground truth transcript. So, for example, a word error rate of 2% means that on average, 2 words are mistranscribed out of 100. And theoretically, a system with a lower word error rate can be said to be better than the one with a higher one. But consider the following scenario. We have 2 systems. The first one has a word error rate of 1.5 that is really good, and the latency of 2500 milliseconds that is not so good. The second one has a slightly higher word error rate, but the latency is significantly better. Even though the first system has a lower word error rate in a real-world setting, the second system is likely to be chosen over the first one because of the word error rate latency trade-off. So before moving on to latency, let's look into the useful subtypes of the word error rate metric and some relevant topics. So the standard word error rate treats every word equally, and it doesn't always reflect the perceived ASR quality. In fact, some words might be more important to recognize than others. So for example, recognizing the word hurricane correctly might lead to more significant outcomes than recognizing the word there. And also, something to be mindful of is that word error rate is not comparable across different languages. A word is a language-dependent concept. What can be a word in one language is a sentence in another. And also, some languages don't even use spaces. Written domain conventions, or the agreement on the rules of the transcription, affect word error rate calculation as well. In the phrase set an alarm for 7:30, 7:30 can be spelled as words or as numbers. That mouse can be spelled literally, or with 5 instead of S if it's the name of the EDM artist. Then there are also options of transcribing kinda as kind of and wanna as want to. And also an important topic in this space is punctuation that can be present or absent in the transcription output. And ideally, word error rates should be calculated independently for various semiotic classes, be it spoken punctuation, time, numbers, names, and others, domain terminology, stop words and other frequent words, different levels of granularity, such as utterances or speaker turns. And even the notion of word error rate could be extended from the top machine hypothesis alone to the list of top and best hypotheses instead. And these modifications are helpful because if we want to explore the distribution of the misrecognitions, the standard word error rate metric is not enough. Another helpful layer would be rich metadata about the individual scores. It would be great to have access to per-word confidence scores to help researchers better analyze ASR models. This is also helpful in the downstream applications, such as dialect systems. For example, if the confidence score is too low, the system might ask the user to repeat or confirm before moving on to the next dialect state. Along with the orthographic spelling, it would be helpful to output the phonemic transcription as well. Similarly, for the downstream applications, it is valuable to disambiguate some words. L-I-V-E can be leave as a verb and live as an adjective. Or even geolocation names. Houston is a Texan city, and Houston is a New York City street, and they are spelled identically. Omitting word times would be helpful for more efficient search through the recordings later on, and for the better alignment of captions with the video. Additionally, assigning utterances to particular speakers, also called speaker diarization, is helpful as well. And for this task, there are already some independent benchmarks. Quite a couple of important speech recognition metrics have to do with the timing. Latency has several different interpretations, but the one that is the most frequently used in connection with the ASR systems is the delay between every spoken word and the time when the transcript was outputted. Relatedly, real-time factor is a ratio between the processing whole clock time and the raw audio duration. It depends on the hypothesis space, where larger hypothesis space might increase RDF, but likely leads to a higher transcript quality. And the small hypothesis space might correlate with a decreased RDF, but possibly by a cost of a lower quality. And for the reporting, it's common to normalize RTF by the number of CPU cores and hardware accelerators to focus on the properties of the ASR system instead. And RTF below 1 is required for streaming ASR models. There are some other important metrics for streaming ASR systems. One of them is the stability of partial results that basically shows how often the recognizer changes previously emitted words. A related metric is the quality of the intermediate hypothesis. How far off from the final guess were the recognizer's intermediate guesses? And pointer accuracy, also known as the voice activity detection, is also something that's important to track to ensure that the mic is open while the user is speaking and closed as soon as they finish their utterance. So there are also some other important dimensions that we will not be discussing in depth here. For example, training-related metrics would track the amount of data required for training and the number of parameters and constraints on model topology and hardware resources. Sometimes the recognition can be biased towards certain phrases, like expecting yes or no as a response, and even semiotic classes. For example, if the expected utterance contains numbers. In cases like this, the contextual biasing can help to improve the overall quality of the ASR system. There is also a phenomenon of so-called ASR hallucinations, when systems output transcript for audio without speech present. This can be studied by looking at the insertion rates that are anyways calculated during the word error rate computation step. And related to this topic is adversarial attacks, when a particular message is hidden in the audio. Humans won't hear it, but the system transcribes it and might trigger some action. A robustness to such adversarial attacks is also a very important parameter. And the final dimension that we wanted to bring to your attention is debugability. How easy is it to fix issues with the system? For example, how easy it is to introduce new words such as COVID-19 and their related terminology? What error rate, latency, real-time factor, per-word metadata, and all these other metrics can be very helpful when trying to compare quality of different ASR systems. Now, in this final section of our talk, let me switch to the topic of understanding ASR quality for different demographics. But before moving on to the particular demographic categories, let us look into the sources and types of linguistic variation. Linguistic variation can take very different shapes. Among them, phonetic differences are sound realizations that are specific to a given accent. For example, if we compare British English and American English, the word pure can be pronounced in different ways. In British English, the final sound is schwa, while in American English it's rhotic. Phonological differences might surface as various numbers of phonemes in various dialects. Similarly, the word letter will contain different number of phonemes in American and British English varieties. 4 phonemes in British English and 5 due to the addition of the word final R in American English. Lexical differences show themselves as terms and words specific for certain language varieties. As an example, in Scots, bairn is a word for child. Differences in sentence structure are due to syntactic variation. For example, one of the features of African American vernacular English is double negation, such as she didn't do nothing. And of course, pitch and voice quality differences that are correlated with gender and age introduce an additional variation to the speech signal. Since the language variation is deeply connected with speakers' dialect, accent, age, gender, and other similar factors, it is important to measure how recognition rates differ depending on users' demographic. Therefore, we need to slice ASR quality metrics for various categories of speakers. Importantly, the ideal dataset should be representative of the target user base. And of course, it is very challenging to get datasets with rich metadata, but it is necessary. As Anders et al. Say in their paper, what we can't measure, we can't understand. Slicing the metrics per population group will help to determine gaps between the groups and push towards closing those gaps. And of course, it is difficult to ensure that the proportions of utterances in the test sets match the population ratios. And because of this, it is useful to reweigh any metrics based on the real-world population stats. Imagine that in some set, 85% of the utterances are featuring properties of the dialect A and 15% featuring the dialect B. However, in the real world, 60% of the target population speaks dialect A and 40% speaks dialect B. In this case, the metrics obtained for those 85% of the A-type utterances should weigh 60%, and the metrics for those 15% of B-type utterances should weigh 40%. The reweighing the metrics based on the real-world population would help to have more representative ASR quality scores. Let's make demographically informed ASR evaluations a little more visual. Imagine that the population is subdivided into three mutually exclusive groups. Group A is 60% of the population, Group B is 30%, and Group C is 10%. On the right side, there are two plots of possible distributions of word error rates across these three population groups. Note that the width of the bars reflect the size of the population groups. So in both cases, the overall word error rate is 10, right? So on the upper plot, for example, if we take word error rate of 6.5 and multiply it by 0.6 and add 13.9 multiplied by 0.3 and add 19.3 multiplied by 0.1, we will get 10. Similarly, we will also get 10 for the plot below. But if we pay attention to the gap between the best performing and the worst performing group, the second plot is clearly better. While the gap is 3.5 word error rate points on a lower plot, it is 12.8 on the upper one, and it is significantly more. Preferred ASR models are more consistent and provide comparable recognition quality for various groups of speakers and language varieties. Of course, you might notice that speakers are likely to fall into several categories at the same time. Consider a 20 to 30 years old female speaker of Chicano English from Miami, right? So there is the age bucket, 20, 30 years old, female gender, Chicano English sociolect, and even a regional variety, Chicano English spoken in Miami. Of course, having data for intersectional groups would be good, but it is really, really difficult to get samples for every category due to the combinatorial explosion. That's why we're suggesting to stick to the mutually exclusive groups, since it helps to generate new insights into the quality of the ASR systems for each slice, without making assumptions about the causal interactions between the underlying variables. Now, let's take a look at some of the important slices for ASR model evals. Regional language variation is definitely extremely important. In the US alone, there are at least three main regional groups: the Inland North, the South, and the West. In our previous work, we showed how regional variation can be explored using cron learning pipelines and discussed the potential impact of the regional variation on the ASR performance. As an example of relevant datasets, consider two call-home sets, one for the Standard American English and another one for the Southern variety. Another source of the linguistic diversity that might impact ASR quality are sociolects, like African American Vernacular English, Cockney English, and so on. And moreover, sociolects frequently also have regional variation. To address this source of variation, one could look into sets such as Coral for African American English and Eslora for Galician Spanish. It is also important to recognize speech produced by non-native or L2 speakers. L2 speech is likely to reflect some characteristics of their native languages, as you might be hearing right now, and data sets such as GNU Speech Accent Archive are extremely valuable and provide metadata, such as native language of every speaker. Numerous studies show that speech recognition rates may vary depending on the gender and age of the speaker. And it is important to look into the ASR quality for different genders and age groups as well. Sometimes this information is not available, but the researchers show that pitch is correlated with age and gender, and therefore pitch buckets can be a helpful proxy. So there are available datasets that provide such self-reported metadata, and Mozilla Common Voice is available in dozens of languages is one of them. And speech impairments can affect the quality of the speech recognition as well. And currently, researchers are exploring ways to collect such datasets. The list we provide is by no means exhaustive, but we hope that it can be used as a good starting point. So, time to conclude the talk. We discussed the following methods to improve benchmarking of ASR systems: bringing real-world usage domains and challenges into speech recognition test sets, using a wide range of quality metrics, and taking a population-weighted approach to measuring ASR quality that factors in the distribution of the ASR performance for various population groups. Of course, it would result in many slices and metrics, and using system report cards could help to organize and present the data outlined earlier. So, we hope that our survey can help to improve future ASR benchmarks. Adapting even just some of the proposed methods will already be helpful, but the list we provide is not exhaustive, and we would love to see future work in this domain. Thank you for listening to this talk, and we look forward to the discussion session.